So our next metric is called the discrete metric. And again, I want to start with a non-empty set X, and I'm going to define my metric D in the following way. By the way, this notation is just function notation. It's saying D is a function mapping from ordered pairs on X to the set 0, 1. And let's point out that this is a subset of the real numbers, the non-negative real numbers. And so that's this works, right? As long as I map them everything to either 1 or 0, then I am certainly fitting the initial criteria that we had for a metric. And so now the question before us is, how does this metric work? So the discrete metric is defined as follows. So it's 1. The distance between x and y is defined to be 1 whenever x is not y, and it's defined to be 0 whenever x is the same as y. And so that's how it goes. And so we should actually confirm that this is a metric. So let's write that down. Let's confirm that D is a metric on X. So we have to check the 3 criteria. So 1 is clear. That's clear, right? Think about it. It's 0. By definition, the distance between them is 0 if and only if x is y. So 1 is clear. Also, 2 is clear. And I want to check 3. So 3 is interesting. So what are we trying to check? Let's write it in a different color and remind ourselves, right? We're trying to check that the distance between x and y is less than or equal to the distance between x and z plus the distance between z and y. Okay, and so we should ask ourselves, when can this inequality fail? Well, if this side is 0, and then these can be whatever they want to be, right? If this one is 0 and 0, we're good, right? If this side is 0, then if this one is 0 and this one is 0, we get 0 less than or equal to 0, we're good. If one of them is 0, the other is 1, 0 is less than or equal to 1, we're good. If they're both 1, 0 is less than or equal to 2, we're good. So there's no problems when this side is 0. The question is, what if this side was 1 and the other two were both 0? That's the only way that this inequality can hold. And so we're going to try to go ahead and prove this by assuming that these two are 0, and then we'll show that one has to be 0 as well. Because if we can't show that, then it won't be a metric. So let me get my eraser on. Whoops. All right, so the pink here is not really part of my formal write-up, but that's fine. I want you to see how I'm thinking about it. So let's go ahead and assume that d of xz plus d of zy, let's assume that side is 0. Okay, well, then what do we know? The only way that can be 0 is if this one is 0, the distance between x and z is 0, and the distance between z and y is 0. That's because everything is positive. In general, if these are allowed to be negative, then this one could be negative and that one positive. But everything is non-negative, and so they both have to be 0. And so what does that mean? So x equals z, and what? Z equals y. We can now conclude that x equals z equals y. And then we can say, thus, the distance between x and y is, in fact, 0. So we can say the only way that 3 can fail is if this guy, the right side, equals 0, but the left side equals 1, which we just showed can't happen. And so we've shown now that D is indeed a metric on X. So this is the discrete metric, and let's just take a moment maybe up here, and let's just play with a quick example. I'm going to squeeze it in right here. So maybe my set X is the set ABC. What's the distance between A and B? Ask yourself real quick. Well, it's 1. And what's the distance between A and C? It's 1. The distance between A and A is 0. The distance is either 1 or 0, so on and so forth. So I'm going to erase that, but I just wanted to make sure that we're clear there. All right, so let's stop this video here, and then in the next video we'll look at another